All right. I don't have all the materials I really need, but we'll see how I can do here. This is section 9A. You'll see I had to print it at home. The formatting got all funky. You can see that it's going to be pretty similar to what we just did in Unit 2. You're talking about slope and so on, so that's pretty similar. You actually should be able to read this problem and answer 1 through 8. This is just discussing here. This is about like sitting closer. Does sitting closer to the teacher give you a higher score? So the teacher randomly assigned the students, and this is the row that they were in, and those are the scores they got in the test. So you can kind of see there is a there's a negative slope. So there's a suggesting that the negative slope should suggest the further back you are, the lower your score is going to be in the test. All right, so like I said, 1 through 8, you should be able to answer on your own. So go ahead and pause the video, attempt to do 1 through 8. It's a review of Unit 2, which you could probably use. And then unpause when you're done with that, and I'm going to go over the answers. All right, unfortunately, to go over the answers, I'm coming back over to Schoology to look at the filled-in notes. For number 1, so I have there's a weak negative linear association between row and score. There's your r squared right there. You can take the square root of that r squared. So if I take the square root of that, which I think I had to do in the other problem, you get 0.217. When you find that correlation, you have to pay attention to the slope. The slope is negative, so the correlation is going to be negative. So it's pretty weak. It's negative. And again, it's not like it's a weak curve. It's just a weak linear between row and score. Here's your equation. Again, if remember, this number right here is your intercept. So this number right here is your slope. We talked about the correlation. Calculate the residual. So you have to find the predicted value. The 76 is the actual. There's the residual. So the predicted score for row 1 is higher than the actual by that. You could say it the other way. The actual is lower than the predicted score by that amount. Okay? Interpret the slope. So for each additional row back, the predicted score decreases by that amount. It's decreasing because it's negative. So that's your, and again, remember that key word there. It's the predicted score. It didn't ask you to do the y-intercept here. The y-intercept probably does not make any sense. It's like saying if you're in row 0, so you can't really be in row 0, so there would be no interpretation there. The standard deviation of the residuals, again, the standard deviation of the residuals is just trying to figure out how spread out your residuals are. So the predictions for scores are off by that amount. R squared, so it's not very high. So 4.7% of the variation in score is accounted for the least square regression line with x equals rho. So rho is really not having a large influence on the score. Why was it important to randomly assign the students to seats rather than letting each student choose his or her own seat? We want to avoid confounding. Smarter students might choose to sit in the front, and I wouldn't know if it was because of the row or because of the smarter student what that was causing the result. All right, what this whole unit is about is figuring out if what happens in the sample would actually also happen in the population. So it says, does the negative slope provide convincing evidence that sitting closer causes higher achievement? Or is it plausible that the association is due to the chance variation in random assignment? So the question is, this is like just one set of tests from the teacher. So is this one set, so in this one set we see like a negative association. Is that just because of chance? Or is it because of the row actually causing the score to, or actually influencing, I should say, the score to decrease? She did do random assignment though, so I could say cause. All right. So again, the idea is that when we were in Unit 2, we were just kind of looking at the sample regression line. And then now in this unit, we're kind of thinking about that, hey, there's this population regression line. So the population regression, so here's your sample one from last unit. It's the y hat equals the a plus the bx. Sorry, it's a little blurry. I don't know that I can fix it really. Maybe if I come out a little bit. All right. You already know y hat's the predicted, a is your sample y-intercept, b is your sample slope. So now what we're doing in this unit is thinking, okay, instead of just having a sample, perhaps we have an entire population. And this is the notation for the line. So they're using alpha again here. An alpha would be the true population intercept, the y-intercept. Alpha is just the Greek letter for a, so that's why we're using that. Then you can see that they're using beta again. So we're using beta, which we've used before. Sorry, my pen got stuck. Something happened here. I'm lagging. They're using beta again. Beta is the population slope. So that's the symbol that we're using for the population slope. Again, you want to kind of think like that on the front two pages there when we were talking about the one sample, like one random assignment of row and test scores, you want to think that if I could take all the teachers' tests and I could put them all together, I could create one population line. Again, we've used those letters before for type 1 and type 2 error. We use them for the significance level. They have nothing to do with that. We're just using the same letters again, okay? All right, so I asked you, it says in the notes to revisit page 468. So if I flip back here to page 468, a sampling distribution. So a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So the statistic that we're interested in for this unit is B, the sample slope. So basically, it's like we have, this is not the same data, but it's like we have a bunch of sample slopes now. So we have a bunch, instead of a bunch of X bars or a bunch of P hats, we have a bunch of sample slopes. So again, it's like if that teacher had all of her test scores and all of the rows that the kids are sitting in, and we just took samples of size 30 kids frequently from that data set there, and we calculated slope, put them back in, take another sample, calculate slope, put them back in. So we have all these little sample slopes. So just like before, we needed to know the sampling distribution of X bar or the sampling distribution of P hat. We need to know the sampling distribution of B here because we need to be able to use the standard deviation to help us calculate a confidence interval or run a significance test on the slope, okay? The mean and standard deviation. Your mean, so the mean of all the sample slopes is the population slope. So remember, that means that the sample slope is an unbiased estimator of the population slope. So that's a good thing. If your 10% condition is met, your standard deviation looks like this. You're not going to have to plug anything into this. You're not going to have to there's some things you need to know, but it's pretty straightforward. Sigma is the population standard deviation of the residuals. So again, in unit 2, we were working with S. S was that standard deviation of the residuals. Sigma would be the true standard deviation of all the residuals. Sigma X is just the population standard deviation of the explanatory variable. And if you notice that there's a square root of n in there. Again, and that's sigma X bar. It's measuring the typical distance between a sample slope and the population slope. Remember, standard deviation is always measuring how far away something is from the mean. In this case, the mean is the population slope, and what we're dealing with is a bunch of sample slopes. Obviously, if you take a bigger sample size, that standard deviation decreases. That's happened before. These formulas are both on the formula sheet, so you don't need to worry about that, okay? This one right here. So if you read the problem here, it's about tropical cyclones, known as typhoon and hurricanes, are intense circular storms that originate over warm tropical oceans. The low air pressure stored with these storms can cause very damaging winds. For the population of the 193 Atlantic tropical cyclones over an 11-year period, so that's the entire population, they have that regression line where X is the minimum air pressure and Y is the maximum wind speeds. The standard deviation of the residuals is that. So that's every single one of them. And the standard deviation of the minimum air pressure, again, just the X, is that. Imagine taking a random sample of 16 Atlantic tropical cyclones during this 11-year period and using the sample data to calculate B, the slope of the sample regression line for predicting Y maximum and minimum, X minimum. All right, so to calculate and interpret the mean of the sampling distribution, and then we're going to do it for the standard deviation. I'm literally just using these formulas. They are on the formula sheet, which I do not think I have here at home, but I promise you they are on the formula sheet. If I flip back over to my notes here in Schoology, so mu b, it's just equal to beta. So if I had all possible samples of size 16 and calculated the slopes of the regression line for each of them, the average of those slopes would be that, all right? So if I could take all possible samples from this 193 of size 16, 16 is less than 10% of 193. I plugged everything into the formula. Remember, it's the sigma over sigma x times the square root of n. If you had all possible samples of size 16 Atlantic tropical cyclones from this 11-year period and calculated the slopes of the regression line for each of them, the slope would vary by 0.084 from the true slope of negative 1.24. Okay? All right, the conditions. All right, your conditions for this one, I don't my whole thing, printing, whatever. Anyways, it's this L. There's more conditions. There's a linear condition. There's a normal condition. There's an equal standard deviation condition. Random 10%. Our 10%, we've seen it before. Nothing new there. Okay, that one's our same one before. So this is the same. Random, same as before. Either you've got a random sample or you've done some random assignments. The normal check, a little bit different here. Similar idea. We're going to have to look at a graph, but we'll talk about that in a little bit. Linear check, we're going to look at the graph. Equal standard deviation, we're going to look at the graph. All right. So there's two things here. There's what we want the conditions to be, and then there's how we're going to check them. So the linear check, we basically want to ensure that we want to try to figure out if the true relationship between X and Y are linear. So if you look at this graph here, if this was, again, this is the population. So the hope is that X and Y are linear. If I'm running a confidence interval or a significance test, I want those two to actually have a real linear relationship in the population. I'm not talking about how you check it just yet. The normal check means that for any given value of X, the responses follow a normal distribution with a certain standard deviation. So what you can think about with the data that we started off with, if this was row 1, the Y's are all the test scores that you could have for row 1. They should vary and they should follow a normal distribution, and they should have some standard deviation. And then if this is row 2, same thing. All those scores from row 2 should vary normally and have some standard deviation. This is row 3, and all those scores should vary normally and have some standard deviation. So again, I'll tell you how you check it in a second, but this is the idea. So the scores for a fixed value of X, the Y variable, which in our starting problem was the scores, should vary normally. Okay? The equal standard deviation is just talking about that they should vary with the same standard deviation. And the random, we talk about 10%, we already discussed. All right, so how do you check these things? So for linear, you can check the scatter plot to check that the overall pattern is linear. You can check the residual plot to make sure that there's no leftover pattern in the residual plot, or there's no pattern. So linear, and again, you're using the sample data to infer something about the population. So we're going to look at the sample scatter plot and hope that it's good enough to infer that the population would also be linear. For the normal check, what we do is we actually look at the residuals. We are looking at kind of what's left over there and just making sure that there's no strong skewness or outliers. Again, we're not necessarily looking for it to be perfectly bell-shaped. We just are going to look at the graph. We're going to look at the residuals, either a dot plot, stem plot, a histogram, or box plot, and make sure that there's no outliers or no strong skew. For the equal standard deviation, we're going to look at those residuals, and we're just going to try to see how they're scattered. What we're hoping for, again, the original stuff was saying we want the population standard deviations to be the same. What we're hoping for here is we're hoping that our residuals are equally scattered. If you had a situation in which here's a picture in the book. This situation right here. So as the X value is changing here, the residuals are getting more spread out. So it doesn't seem that the standard deviation of these lower X values would be the same as the standard deviation of those higher X values. So you kind of want something that just has equal scatter. The random check, again, either you have a random sample or you have a, oops, I lagged here. I'm back at the paper, but my camera's not. See if it comes back. It should eventually. Maybe if I switch the screen. Nope, there we go. Let's go back. Oh no, now I've lost it for good. Oops, still on the book. It doesn't help if I hit it. Well, let me go back over here. We'll see if it comes back. Your random. See if your data was produced by a random sample or random experiment. I switched it, but this should just be not less than or equal to. So if you have one sample, you're just checking that. If you're randomly assigned, like she did with the students to the seats, then you're good. Okay. All right, here we go. Let's go back here. All right. View full screen. All right. See how I said I switched it there. Okay. All right. All right. This is so using Fathom. It's a statistical software package. They did the least square regression. They did the analysis here. This right here is your scatter plot. So you can see there's your row versus your score. Here's your residual plot, row versus the residual. This is a histogram of the residuals. So when we check the conditions, the linear one, I can use either of these two graphs. So if you notice over here, I said the scatter plot is roughly linear. The residual plot shows no pattern. You don't have to write both of those statements. You can just write one of them. I just wrote both because I wanted you to know either one of those are acceptable. For the normal check, I look at the histogram of the residuals. I'm just making sure there's no strong skew or outliers, so we're good. For the equal standard deviation, the scatter of those residuals is about the same, so there's equal scatter of the residuals above and below the residual equals 0. Random, it's randomly assigned, and the 10% I don't need to check because of the random assignment. Okay? All right, this next stuff right here. Obviously, just like before, when we calculate a confidence interval, we need the standard deviation of the slope. Just like before, we run into issues because we're trying to estimate something about a population, so we probably don't. If we had the population standard deviation of the residuals, And if we had the population standard deviation of the x variable, I probably wouldn't need to calculate a confidence interval because I probably already had the real values. So since we don't have those values, once we plug in the statistics, we call it the standard error. So here's your standard error. So your standard error of the slope is S. So that's that standard deviation of the residuals, the S of x. And then again, since we know this is going to be a little bit biased, we're going to divide it by the square root of n minus 1. So your formula, remember, it's the statistic plus or minus the critical value times the standard error of the statistic. So in this case, the statistic is B plus or minus the T star. The critical value is coming from T star. And the SB is this formula. Now, I have never seen a problem where they made you plug everything into the formula to calculate the SB. It's either in the computer output or it's going to be like you'll type the numbers into the calculator and you'll get the answer that way. The T star here, the degrees of freedom for this one is n minus 2. It's not n minus 1 like it was before when we used T. The best explanation I can give to you for that is that we just have two variables. So therefore, just remember n minus 2, okay? All right, caution on 814. All right, so this is where kids get confused. It says the values of t given in the computer regression output are not the critical values. All right, so here's our table that we've seen before. Now, you can always cross this one out. In this unit, you can still cross these ones out. You're actually not going to use this number either, but I'm going to tell you what it is. Remember, this is your remember the first line, intercept, second line, slope. This is the coefficient, so this is the actual intercept. This is the actual slope. This right here, this is your standard error of the coefficient. So this number that I crossed out would be the standard error of the intercept. You can actually do inference on the intercept too, but we don't do that in AP. This right here is your SEB. I sometimes call it the SEB. The book called it SB, so either one. So there's your standard error of the slope. What that caution was saying, this right here is not T star. This is actually the test statistic if you ran a significance test, and this column is the p-value. We will talk about that in 9B. All right, so I'm going to flip back over to the other paper. So interpret the standard error slope. So if we had all possible samples of size 30 from this population and calculated the regression line, we'd estimate the sample slopes would vary 0.9472 on average from the two slope. Remember that standard error is just trying to tell me how far away are the sample slopes from the population slope. All right, when we do the confidence interval, I'm going to switch back over to my other screen here. So remember, it was B plus or minus T star times that standard error of the slope, and I think the book used SB. The B is right there. T star, I'll get that in a second. This number, there's your SEB. Okay, so to get the T star, remember T star is, I don't know what the heck that's about. T star is always the area to the left. If we are doing a 95% confidence interval, the area to the left of this one, stupid. The area to the left of that side is 0.025. The area to the left of this one is 0.975. The degrees of freedom, again, are n minus 2. There were 30 minus 2, so your degrees of freedom are 28. So when I go do my inverse t, second bars, inverse t, point, you can do the 0.025, 28. If you wanted to do the other boundary, you'll just get the positive number. Remember, ignore the sign. You already got a plus or minus in the equation, so ignore the sign. Just put the number in there. And that's what I have back over here. So there's that 2.048. You do all the math there. There's your interval. So then I can say we are 95% confident the interval negative 3.057 to 0.8228 captures the true slope of the least square regression line with x equals rho and y equals score. Based on your interval, is there convincing evidence that seat location affects score? No, since 0 is in the interval, it's possible there's no relationship between score and rho. So again, 0 is going to be that important number for us. 0 is in the interval. 0 would mean that there is no relationship between the two. All right, you have a 4-step process here. So I kind of I abbreviated it here just because I was already kind of long with these notes. But in your 4-step process here, first step, I want to find whatever percent confidence interval for the true slope. The name of this one, so to answer this question down here, the name is the t interval for the slope. We checked those conditions previously. You either use the computer output in the formula like I just did in that last example, or you use g ln reg t int. And then you would conclude in the context of the problem. The tip on page 816 is talking about how you shouldn't just automatically assume you're going to have to type in numbers. Sometimes they'll actually give you the computer output and you won't need to type in the numbers. This problem is not that case. So what I did here with this problem is we are going to type in the numbers. I'm going to do that real quick here so then I can show you the calculator command to find that. While I'm typing those in, you can either also type them in or you can read the problem and figure out what this one's about. I just typed in the same numbers twice. My eyes are playing tricks on me. All right, let me just make sure I have the right numbers typed in before I show you everything. All right, perfect. I'm a great typer. All right, so this one. So again, that's step 1. 95% confidence interval for the true slope relating y, average SAT score, to x percent free reduced lunch. Okay? T interval for the slope. So there's my name. Linear. Scatter plot's linear. The residual plot shows no pattern. Again, you only need to mention one. The dot plot of the residuals shows no strong skew or outliers. Again, not looking for perfection here, not looking for it to be bell-shaped. Just want to make sure we have no strong skew or outliers. The scatter of the residuals is about the same. So the scatter is about consistent. I mean, it's a little bit bigger here, but it comes back down. So it's not like consistently getting bigger. And it was stated here that it was a random sample. And since it was a random sample, we check the 10%. So 16 is less than 10% of 500. All right. Should do this on the calculator. All right, so I'm a little bit slow here. You can see there. Oh no, I have the rainbow circle of death. All right, well, the rainbow circle. Nope, came back. All right. Let's see if this catches up to me. We are going to use, as you can see at the top there, it says G is the Linreg T-Ent. You find that by going to your usual place, your stat, and then over the tests. It's towards the bottom there. It says G says Linreg T-Ent. You would tell the calculator, there's your L1, there's your L2. Frequency is 1. Your confidence level is 95%. You don't, you can change that to, whatever it is. And this one is 95%. Regression equation, whatever. Hit calculate. There's the interval. All I ask is that you give me the interval, give me the slope, and give me the intercept. That Linreg T-Ent, it gives you other stuff too. It gives you the S, it gives you the R squared, it gives you the R. So it does give you other things. I just want you to give me the interval. I'm going to flip back over here. So I think I had, I also asked for the degrees of freedom, and the S, I guess. I think I had A written here, but my pen must have erased. Those erasable pens, if you put like heat on it, it'll also erase. So I probably had A. A was 1,1242.48. There's your B, there's your DF, there's your S. So then here's your statement. We're 95% confident the interval, negative 4.806 to negative 2.914 captures the true slope of the regression line relating y equals average SAT score to x equals percent free reduced lunch. All right. So that was 9A.